So here's what we did yesterday, just as a reminder. We're starting in this unit. We'll get to it today, we'll start to define the derivative. We won't see the rules for a couple more lessons, but the derivative, again, it's one of the biggest concepts, especially in Calculus AB or Calc 1 if you're going to college. And it continues to be important throughout. So anybody taking physics, like AP physics? Or took it? Okay, so did you ever see derivatives in there?
No.
Okay.
Well, here, we took algebra phase.
Okay. If you do any kind of engineering in the future, if that's you, then you'll be doing calculus-based physics, which a lot of the relationships in physics 1, is derivative stuff. So think velocity, acceleration, those are just derivatives of the position function. So that said, let's do a quick review. Yesterday, let's do it this way so it's bigger. Look at that. I twisted and it just loses connection somehow. Stupid. Yay. All right. So average and instantaneous rates of change. Guys, a derivative, I'm going to say this a whole bunch, and pretty soon you'll be like, shut up, I know by now what it is. A derivative is a rate of change. It always will be, okay? Derivative is the slope, and so that's why we're writing about slope and getting more familiar with that. Remember our kind of better notation, maybe I'd say, the f of b minus f of a, we saw that develop into two difference quotients yesterday. So we just talked through slope, did some average rates. I do want to remind you that anytime you're in context, make sure that you have your units on there. This one wasn't, but if it is, make sure that you label that. Okay. The big idea from yesterday that we got to were these two difference quotients. I circled them in pink. We will very shortly edit the first one, so this one on the left, to instead of saying A, it will say X, and that kind of generalizes it a little bit more. But note that in one of these, we're thinking through, I showed you that graph where you could play with the points. We're thinking through adding some random H value to move to the next point. And then in the second one, we're just, like this one on the right, we're just talking about two values. It looks more like the average rate of change that we're used to. Does everybody agree with that? I personally, I put a star by this one. We use it a little bit more. And in some cases it's better. In some cases you probably won't like it as much. It just depends. So that was the background. Let's just quickly remind you what these say. Remember, I kind of did it over here, so let me use this picture. As we take this point or any point on the curve closer and closer to our original point, that H value becomes closer to 0, and we're approximating and becoming the slope of the tangent line, right? So like right now, my slope would be, what's that kind of line called? It's giant, but what's it called when we connect 2 points on the line? Yeah, it's the slope of the secant. The closer we bring that second point over here to this one, the closer we get to the slope of the tangent line. The derivative is the slope of the tangent line, okay? And again, we have so many different functions out there, whether they're real world based or mathematical. So part of our goal in this unit is to know how to do derivatives of lots of different things so we can find those slopes. So that was kind of a recap of yesterday. Both of these, and especially this first one, but both of these are essentially the definition of a derivative, okay? We're going to do that today later, but actually let me just go here to remind you what we did next. So flip your page over. It says find the instantaneous rate of change, okay? I want to remind you, because I didn't read that yesterday and I probably should have, but that whole thing is the slope of the tangent line. The instantaneous rate of change at a point, right? At x equals -1. That is specifically the slope of the tangent line of this function at x equals -1. And so we worked through plugging in that our starting value, or the point we're interested in, is -1. And then h just represented that change in x coordinate between the point we're interested in and the next point that we wanted to take to nothing. Okay, so bringing that point closer and closer to the point of interest so that our slope is a tangent line instead of secant. That's what that is. Okay, so we plugged -1 plus h as a plus h, or x plus h, into the function, and then we plugged in just -1 into the function. So back here, plugged in a plus h, and then just plugged in a, and then worked through stuff we learned all in the last unit to figure out that limit. Okay, so after, tell me if this isn't working for you, but after that step, the rest of that problem was last unit stuff. It was trying to figure out a limit that was indeterminate. Okay, in case that was unclear yesterday, the goal was kind of new. The goal was to figure out the slope of the tangent line at a point, but we set it up there, and then the rest of it was just using our limit strategies to figure out an indeterminate limit. Okay, which was algebraic manipulation. That's what we did. And we got 3. That was using that first difference quotient. Now we're going to do the whole thing again with the other definition, the other difference quotient over here. Okay? So we just plugged in x for f of x, like that. It's just f of x. It's the function itself. And then we plugged in our 1 for f of a. And here we are kind of midway through. Does everybody feel caught up from yesterday? So again, we're finding the slope of the tangent line at x equals -1. We're just doing it with a slightly different version of our slope formula called a derivative. Okay? So let's finish working through that. At this point, what have we done to get to this line right here? Like, just describe the process we've taken to get there. Yeah, we just, like, this blue piece became 2. We saw that on the first version. And now we're just going to combine our terms, like basically just working through algebra, right? Pretty basic algebra. Everybody following? It's okay to say no. What can we do in the numerator from here? Do you see how our limit currently is indeterminate, right? Go ahead. Factor, yeah. Now, it doesn't look like it's in the right order that we're used to, so maybe rewrite it. But we have -x squared. I would definitely factor that guy out. Unless, just thinking through this test, I think most of you are factoring pretty well. There was a couple issues, but most everybody, I think, is doing okay with that. So all I did was just pull out the negative and then reorder in the normal order. I want to pause here and say this, just because I'm going to mention it tomorrow when we talk about the test, but we might as well start today addressing this issue. A lot of you are really, really messing up this whole thing, the limit notation. Either missing writing it at all or writing it when you don't need to. When do we use limit notation? Like, let's just take this problem I just circled. Do I need limit notation all the way through here? Let's ask that question first.
Yes.
Okay. When is it okay to stop writing limit notation?
Like right before you get the answer.
Be more specific, because
Like-
but right before the answer is a little vague.
Like the equation that you get the answer.
So when you
Be
plug
more
in
specific.
x values,
Yeah, Yeah, thank you. When you plug it in, right? So from here to here, the transition became, I am now going to substitute 0 for h, right? And so now I'm dropping the limit and actually calculating the limit. So I saw things on your, and you don't need to write this on your packet, but I saw answers like this. Why is this too big for the screen? That's annoying. Like, let's say limit as x approaches 2 equals 5 or something. Do you see how that doesn't work? Does that look familiar to anybody? Okay, I think there's quite a few of you doing that. Just drop the limit when you finally plug in and it doesn't become part of your answer. So over here, now back to the one we're working on. Can we drop the limit yet? No, because we're still just manipulating it, right? We're just rewriting it in different terms. So my next line keeps the limit. What is the factored form of the numerator?
X plus 1 and x minus 3. Minus 3.
No, it's not 3.
Oh.
Yeah. Okay. So obviously we can cancel the x plus 1. So next question, do I drop the limit yet? Okay, we're going to drop that off. The common factor, I mean. I don't need the denominator now. Let me rewrite that. Don't forget that negative sign, though, floating around. Okay, now what? Think notation. Let's keep that in mind. Equals. Now we can drop the limit, right? Because we're about to plug in. So negative and then -1 minus 2, which is 3. So drop the limit when you plug in. Don't do it before that. And don't write the limit on the 3, because that would be wrong too. Okay, but let's go back to current material, which is to say both of these definitions gave us the same slope. Okay? And I think I'm going to continue to reiterate that. This is the slope of what? Of the tangent line where? At x equals -1. Okay? All right, somebody had a question. Yeah.
How come you can't put 1 as x approaches -1 equals 3? How is that wrong?
Because, so she asked this. She's saying, why can't we write it like that?
Yeah.
What is this limit of? Some function, right? So if we said f, if we stuck an f in here, that would be better. Yeah, in this case, f was defined. But like on the test, most of it never had an f. It was just some expression, right? So not having the f, we're saying the limit of something as x approaches -1. We have no idea what that is.
So would we have to, how come we can do the equals on like the same line then?
How come you can't or can?
Can.
Here?
Yeah.
Like, why was I able to put that equals there?
Yeah.
Oh, okay. Because we're transitioning now from this. I'm going to circle a big chunk of stuff. All of that is the same thing. It's just, it takes our brain and our eyes time to see the expressions expand and then factor and cancel, right? But this last line, this one, is perfectly equivalent to that one. It's just got some algebra done to it to clean it up. right? It's not until we step outside of that over here that now we're no longer rewriting it. We're actually evaluating the limit. So we're solving, I guess you could kind of say. Does that make sense? Okay. Thanks for asking that. So here's the good news. You're not going to have to really do this big chunk of work after the next couple sections. In this one we do. Because it helps us to see how we can define the derivative. Here's something that you might like to know. Here was our... I think I'll wait on that. Never mind. I don't want to get too far ahead. Okay. These ones are kind of tricky, but these, unfortunately, are AP style questions. So these are ones you want to study. So it doesn't have to be. I feel like sometimes it's hard to see. Let's read the directions. Identify the function we are working with. Then identify the x value for the instantaneous rate of change, slope of the tangent line. Okay? So look at this first one. And which of the two of our difference quotients is that form? And you might want to flip to the other page, the first page, if you don't remember. So which of the two forms of our difference quotient is that? It is the first one, okay? So I think it's worth putting that down. This is limit as h approaches 0 of f of... I'm going to switch it over to x plus h, just because that's what we're going to see here in a second. Okay? That's this form. We can tell, number one, because it has an h in it. That's basically the easiest way. Also, because we are not approaching a value but 0. We want that distance between our x coordinates to become 0. That's what h represents. So, let's look at this thing and compare it to just the plain form down here and see if we can figure out what the function itself is. Remembering that this has stuff plugged in. Okay? So, do you see how we have a 5 and a natural log? That's definitely going to be part of our function. Okay? And then where did we plug something in this first term? Okay, yeah, when we either x or a, we did plug that in. What else? Where? I'm saying where did we plug it in?
The denominator.
The denominator, right here. Do you guys recognize that that chunk is the x plus h? Okay. And I feel like this is going to get busy, but I'm going to try it. This is x plus h. So if you go back, just to remind you, if we go back to the example up above, x plus h was plugged in for every x, right? At that time it was negative 1 plus h. So down here, that's the only place we plugged it in was in the denominator, which tells us that our function is 5 natural log of what? 2 over x. How do we know that? Because we plugged in x plus h for every x, and that's the only spot that we saw it. So that has to be our only x in our function. Everything else has to, that's just part of the function. I see confused faces. Ask some questions. Let me know. Yeah?
So, since it's set up as f of x plus h minus f of x, why is 5 natural log 1/2 the second half?
Okay, that's what we're going to talk about next. So any other questions on this first part? Do you see how if I said, it's kind of thinking the backwards version. If I said, please go evaluate the derivative of this function or take the instantaneous rate of change, your first step would be to plug in 4 plus h into that x, right? If we were looking at x equals 4. Yes?
Yep.
Okay. Which I kind of just gave away the second part, but that's okay. So where are we looking to evaluate this derivative or this instantaneous rate of change? At 4. There's two ways you can see that. Excuse me. This 4 right here is x plus h. It's the x of x plus h. Okay? But also in the second piece, f of x, it says is 1/2. Right here. We know our function is 2 over x. So you could kind of set up a little equation, 2 over, I filled it in already, 2 over x equals 1 over 2, right? Because that we know that inside those parentheses is a half, and we know our function is 2 over x inside of there. And just solve that little proportion. You guys remember how to do that? Like just cross products, right? So x equals 4. So we can see that kind of two ways. Does that feel confusing? This form is worse. It's more confusing than the other one. Let me show you what I mean. Does everybody see this second example is the other version of the difference quotient? So go ahead and write this one down underneath. I bet you can do this one a little bit better. Where are we evaluating this limit? Let's start with that one. So instantaneous rate where? Pi over 2. That one jumps out a little easier, right? And then what's the function? Okay, this is much easier. F of x is the first thing in the difference quotient. So what's our function? Just sine of x. So this is why one of the reasons I said you might like this form better sometimes is because of these problems. It's definitely easier in that. Any questions on that one? Okay. I'm going to give you a little bit before we move into the next section. I want you to try these. So, excuse me. So go to 21. And let's just do that section right now in class. So 21 through 28. And what do you think, 10 minutes maybe? Does that feel like enough? It's enough. So 12:55. It would be cool if we could get done before that, but 12:55. Everybody find it okay? Okay, first one. Which form?
2. Second.
Yep. And I'm going to write form 2, but that's not an official thing. It's not like the name of it. So remember, f of x is just the first part. It's f of x minus f of a. So it's just 1 over the square root of x squared minus 2x. And then where are we evaluating this one? At 7. Okay. Same thing. F of x is just that first piece. So 3x minus 9x squared. And we're evaluating it at -2. I'm going to jump to 25 since we're kind of on a roll with this type. So f of x, 6x squared minus sine x. Oh, no, not minus, just times. 6x squared sine x. Evaluated at pi over 2. Okay, let's do the H ones. Actually, sorry, there's one more of these. Okay. So 1 over root 3x at 5. Okay, let's do these other kind. Let's look at 23, I guess, first. Quick way to do these, or quick way to think through them. Anywhere you see something plus h is an x. Okay, I'm going to write that up here. And hopefully you guys go back and study your notes, like look over these. That's what I would highly recommend that you do. Actually, I'm going to write it more like this. Something plus h is an x. So I could rewrite this with an x there. And so what's our function? Three natural log of x. Okay? And then the number with h is the point. So an x equals, in this case, 2. Seem okay? Pretty okay? All right. Let's try the next one. What do you see? X, like 1 plus h is getting substituted for each x, right? So our function becomes what? 3x squared minus 7x plus 1. How do we know the plus 1 is part of the function?
Because it doesn't have parentheses. But like, it's before the split of the other parentheses.
Yeah, in this case it has parentheses around the 3, which helps, right? It may not always.
What is the 3 doing? Like, what is it?
Okay, so he's asking, what is this 3? This is f of 1. In this case, yeah. So that is f of 1. So it's the minus f of x at this point, or in this one, x is 1. So it's f of 1. Anyway, that tells us that x is 1. That doesn't look like a 1. Okay, next one. How about this one? Kyla, tell us what this one is. Or just tell us what the function is. You can tell us how if you want, but
Log of 2 minus 4x.
okay, so we see that h minus 5, that's going to be our x. It takes the place of x, I mean. And so inside of this whole thing, it's 2 minus 4x. What is the minus log of 22? What is that? Oh, I see what you're saying. It's f of negative 5. Yeah, good. Okay, so again, we're evaluating this one at negative 5. How'd that one go? It was a little weird. Okay. Did anybody do 28?
Yeah.
Okay, so let's check that one. Again, we look for where the h is, what's with the h, and then we replace that with x. So what is our function in this case? E to the 6x plus 1. Good. And we're evaluating it where?
3.
At 3. So what is this weird e to the 19th, I think it says? Be specific. That is f of 3. Okay? Is this helping? Do you feel like you can interpret that a little better now? Okay. So tonight, I want you to do, huh? What'd you say?
I said we steal the moon.
Nice.
Tonight we steal the moon.
Let's do 16. So do 16, and then let's see what the test prep has to offer. Yeah, let's do test prep. So 16 and the test prep. Okay. We'll check in on these tomorrow. We'll talk about your test tomorrow. That'll give you a chance to ask questions. But let's go ahead and talk about, finally, the derivative. This is a big deal. You've heard me say that already. And gosh, it has so many applications in science and math. So we'll come back to that later. Here we are. I want you to, if you're a highlighter or a circler, I want you to make sure this stands out to you, okay? And anytime you get mixed up or forget what a derivative means, I want you to come back and read this. I think you should be coming back and reading this anyway, to be honest. You can't remember everything that we learn the first time. So, derivative. The name doesn't totally imply what it is, which is unfortunate, but it's an expression that calculates the instantaneous rate of change of a function at any given x value. So think about this, applications of this out in the real world. We could find the rate of flow of the Colorado River at any given moment, or the rate of a car in the middle of a crash at any moment, right? Like 0.2 seconds, 0.3 seconds. How is its speed changing? We could calculate the rate of change of the stock market at any given moment. I mean, there's infinite different applications of this. The slope of the tangent line at a point, okay? It can't really be overstated. Now, being that it's a slope, what kind of units does it have? Are you guys with me back there? Are you with me? Am I right in your way, Chloe? Sorry. Just let me know anytime. So use appropriate units. Guys, what kind of units are common for rates? It's a rate, it's a rate. So what kind of units are you going to hear? Yeah.
Like miles per hour?
Yeah, per, right? You're going to hear something per something else. That word per is going to be in any unit label that you put on a derivative. Okay. Here's our very friendly little parabola function, x squared. This, you're going to know pretty soon, like probably next week, how we got from f to f prime, which is derivative notation. I'm going to give you that. If you looked ahead at all, you'll see notation is coming. But that is derivative notation in one version. So the derivative of x squared is 2x. That's the equation or the expression for the derivative of the x squared function. It's 2x. It's being given. So what is f prime of 1? We're going to see this just below, but f prime is the derivative of f. What is f prime of 1? Don't overthink it.
2.
It's 2, right? 2 times 1 equals 2. All we're doing is plugging 1 into the derivative, the function. Okay, here's what it means. If I go over to 1 on this function, that has a slope of 1. And even though I can't draw a perfect straight line, can you see that it's up 1 over 1, up 1 over 1? So that's a slope of 1, right? Our derivative told us that without us having to calculate it. Slope equals 1. Okay, what's f prime of 2? 2 times 2 equals 4. So now we go over here to 2. There's that point, and we take the slope. Notice it's steeper there, slope of the tangent line. It's definitely steeper at that point. And it's telling us that the slope is 4. Which, if I did my line at all correct, it's roughly 4. Okay? What's f prime of negative 2? 2 times negative 2 is negative 4. So we come over here to negative 2, and we draw our tangent line, and there's our slope. I drew it too long. There's our slope of negative 4. Pretty cool, right? Again, you're going to learn how to find the fact that the derivative is 2x, and it's so easy in a couple lessons. But now that we know it, we can find the slope of any dang point on that whole thing. It's very cool. All right. If f prime of x is 5 over x minus x, find f prime of 2. So what do? Just plug in 2, right? So it's 5 over 2 minus 2, which is what? Or we could say half, right? 5 halves minus 4 halves. Explain the meaning. What is 1 half? What does that mean? The slope of what? The tangent line of f of x, where? At x equals 2. So we don't really know what this function looks like. I mean, we could go graph it, but we know now that at 2, the slope of that thing is positive 1 half. Okay? I forgot to write the word line, sorry. There we go. Okay? This is a little unit check. If f of x represents how many meters you have run, and x represents the minutes, I personally would underline meters and minutes. Describe in full sentences the following. Who wants to take on f of 8 equals 1500? Yeah, Judd, go
In
ahead.
8 minutes, I ran 1,500 meters.
Say it again.
In 8 minutes, I ran 1,500 meters.
Okay. I'm going to change it actually just a slight bit. I ran 1,500 meters in 8 minutes, which is just a slight change on what you said.
It's just better grammar. I didn't do it.
It's okay. All right. Who wants f prime of 3 equals 161? Uh-oh. Trevor, give it a shot.
The average rate of change.
Nope.
The derivative.
Nope.
Okay.
First of all, derivatives. Go back up to the top. Is it average? Derivatives are instantaneous rates. Good. Yeah. Annie?
At 3 minutes, I was running at a rate of 161 meters per minute.
Whoo, good job.
That's good.
Does anybody, we should think about if that's a realistic number. Running at a running. I should probably not talk and write at the same time. 161 meters per minute. There's the nut, or the U in the nut, right? Units. Nice. Let's see. 161 meters would be 500 feet in a minute. What's a good?
That's pretty fast.
That's 3 meters. That's not even 3 meters per second.
It's kind of like running, like
I could
taking a minute to run a third of a lap, like a track.
Oh, right. I forgot we could think of it as track. So this would be like half a lap in a minute. That's pretty slow.
Less than half a lap.
Yeah. Never mind. That's pretty slow. Okay. That does not look like slow. It looks like skew. If I could write, that would be awesome. Slow. This is Sonia's rate, right? No, she's fast. How fast do you run? A 400. Do you do that?
I have run a 400. It's not my main.
But you run like 5Ks.
Yeah, and like 2 miles.
Okay. So 5K is 5,000 meters. And what?
How fast?
Yeah, like what's
19.
19? So yeah, that's way faster than this. Good job. All right, notation.
Proud of you, son.
This is, I'm putting stars because it's new and it's important, but you'll see it enough that you'll be like, oh, I get this for sure. So notation, we have Lagrange is how you say that. Some people say Lagrange, but that's not correct. This is named after a guy that was his last name. And that's the one we've been seeing. Okay, f prime of x. So that apostrophe tells us that it's derivative. You'll probably have a favorite out of these two, and I'm hoping that you'll be flexible because sometimes one is better than the other. So f prime sometimes is the way to go. Or if our function was not an f, what if it was defined as y equals? Then our derivative would be y prime. The prime tells us that it's a derivative. Okay? When we do double derivatives, we're going to have f double prime, which means it's going to look like 2 tick marks. If we did 4 derivatives, then it would be y4. Okay, we end up not putting 50,000 tick marks up there, but anyway. Okay, so y prime, maybe it's a function in context. Like I said, the river flow rate, maybe it's r prime for that or something, okay? All right, Leibniz notation. Do you guys remember his name from the first day?
Yeah.
If not, that's fine. He was the other guy that challenged Newton for credit. dy dx. Okay? Or maybe it's df dx. I'll put some more on here, but here's what this says. The derivative of y, some function y. And I think this phrase gets lost on you guys a little because you use it differently. But we say in math, with respect to x. And it doesn't mean like we're showing it respect. It means as a function of x, like depending on x, that kind of thing. So the derivative of y with respect to x. Okay, what would this one say?
Derivative of f with respect to x.
Yep, the derivative of f with respect to x. So df dx. Okay, it could be, we're going to use this for lots of variables, this form more specifically. Maybe we do like a radius of a sphere or a circle. We'll have dr dt. What would that one, do you suppose, mean? Yeah, probably like yep. So the derivative of r, the radius, with respect to time. So one of our problems later will be a circle is growing as more, I can't remember what it is. It's like something spilled and the circle is growing of the whatever it was that spilled. Okay. How about this one? dv dt. That's a big one. Where v is volume. Okay, we end up doing problems where our tank is leaking. So the volume changes, or maybe it's filling up. The change in volume with respect to time. Make sense? Both of those mean the same thing. In fact, Newton came up with his own, but we don't study it in this class. You might see it in a physics class if you ever take that. Okay. Definition of the derivative. I've already mentioned it now a number of times. Do you remember what it is? We saw it in the last section, actually. This is the mathematical, not conceptual definition. Here's it. Here's that one. X plus h, sorry, minus f of x all over h. So remind me what this is doing.
Instantaneous rate of change.
It is. It's the instantaneous rate. But remind me what the plus h does. How does that even make it instantaneous? Can someone sort of summarize the whole last section? Pedro? Why is there a plus h? And why is h involved at all?
It's like to get basically like to see velocity along to I'm like yeah to get to like each is zero.
Why?
Like the difference is zero, so how
Yeah, there you go. So what?
so that like the difference is zero.
Guys, if you can draw this picture without me drawing it for you, then you're getting this. Okay? So I would practice that. Okay, we want to bring this point closer, bring closer to x such that, such that h goes to 0. So we have the slope of what? Tangent. I need to bring that up for you, sorry. Line, not the secant. That basically summarizes the whole last section. So if you can explain that to me on a whim, like I just asked you, then you're getting this. Okay? That's the definition of a derivative, is bring those points closer and closer together using limits, because we can solve for limits. We can't direct substitute. Why? What happens if I just stick 0 in there? It's indeterminate. We have not gone anywhere in our function, right? We're dividing by 0. So we take the limit because it says get closer and closer and closer, and then you have the slope of the tangent line. Okay? Can you guys please study this tonight? This thing we just wrote? Because I promise if you just focus on the procedure of it, like, oh, I can do it, and you don't get it, it's going to be harder. So study this, please. I want everybody in here to be able to explain where the definition comes from. All right. Get ready for some writing. This is going to be a lot. Here's what's frustrating. We'll do this once, well, twice, because there's 2 of them. And then you'll be like, I never want to do that again. This, when I teach you the derivative rules, the derivative of this will take you literally 1 second to figure out. Maybe 2 seconds. Okay? It's about to take us 5 minutes. But it's going to help you conceptualize what the derivative comes from. Okay, so we're going to use the definition, this thing right here, definition of derivative, which is what? By the way, when you start writing, start over here, because it's long. What's the definition? The limit, as, look at it, we just wrote it. Limit as h approaches 0. We can read of that whole thing, okay? Goodness gracious.
The limit of s approaching 0 of
Okay, I am a notoriously frequent big writer, and it runs out of room, so I'm going to do my best. Limit as h approaches 0 of, ready? 2 times what? Yes, x plus h squared minus 7 times x plus h plus 1. Now what? Go back to your derivative definition. We just did this part. So what else do we have to do? Minus f of x minus, and I would use brackets. Do I need to raise it up? You guys need to tell me. 2x squared minus 7x plus 1. All over our friendly h. Okay, listen. My son's taking calculus at CMU, and he just tested on this, and he forgot. Hopefully he doesn't mind me saying this, but he forgot to write the h. Actually, he didn't forget. He said, I know it's going to cancel out at the end, so I'm just going to do all the algebraic manipulation on top and cancel it at the end. His teacher gave him no points, even though his work was completely right. Okay? It was completely right, and it was fine. So he was irritated about that last night. I'm going to do the same thing, just so you know. Okay? So please don't just skip steps. Let's get it all written in here and do it right. All right. We are done filling out the definition. What's our job from here out? It's to be able to solve the limit, right? Yes. Because why can't we right now? Okay. It's indeterminate. So we need to write limit as h approaches 0. Okay. Let's go do this binomial expansion. We get x squared plus 2xh. Or you could do hx. Yeah.
Are we trying to find the tangent line of a specific one right now?
No, we're actually taking the derivative of this function. Okay, so I'm glad you asked. This function is a parabola, right? Everybody see that?
Yes.
This is just some parabola. What we're doing is working through to find an equation of the slope of the tangent line that we can plug in any point to. So just like we did right up here, the equation for the slope of any tangent line was 2x. Anywhere on here. So that's what we're working to find. Okay? We're working to find the equation. Let's just write that. Thanks for asking that. So this is not for the tangent line itself, but for the slope of any tangent line. Okay? So an equation or an expression, maybe you could call it, for the slope of any tangent line at all. And it will boil down to look like a little equation, kind of. Does everybody get where we got x squared and 2xh? Okay, and then plus h squared minus 7x minus 7h plus 1 minus 2x squared plus 7x minus 1. So all we did was just a bunch of algebra, simplifying, expanding, that kind of thing. Okay, do you see why he wanted to leave off the h? But draw your big line and put an h there. It's got to be there. Otherwise, we're not doing what the derivative is defined as. I forgot a parenthesis here after the 1, so put that in there. Okay? Any questions on that line? Are we good where all of it came from? Also, please make sure I don't mess up, because that's definitely a possibility. All right, next line, limit. Have we substituted yet? No, so keep writing the limit. 2x squared plus 4xh plus 2h squared minus 14x minus 14h. Uh-oh. I did mess up. You guys didn't catch it. You did. I put the stupid parenthesis in the wrong spot. Thanks for waiting for 5 minutes.
It was like 5 seconds.
I know. Leave me alone, Trevor.
Oh, well, yours is correct.
All right, plus 1. Parentheses were supposed to go right here. Sorry about that. Does everybody see the error? All right, it's me talking again. Why can't we plug in right now? Why can't we plug in right now? Still indeterminate. Okay. All right, what can we do with this? Now, this is all algebra, right? Like, what we're working through is calculus, but a lot of it is just algebraic. Do you see how we have a 2x squared and a negative 2x squared? Okay, that's good. 4xh, that's not going anywhere. We have a 2h squared, that's not going anywhere. We have a negative 7x and a positive 7x. We have a positive 1 and a negative 1. So that was a good step. That helped. Can we drop the limit yet? No. 4xh plus 2h squared minus 7h over h. Do you see what we're doing next? Remember, we're working to be able to evaluate the limit. We still can't plug in, but we're close. So what would a good next step be? What was it? Factor h out. Can we drop the limit? No. Okay. Now can we drop the limit? So let's show the h's cancel. Now we're going to substitute. So we drop the limit, okay? So now it's going to be 4x plus, not plus, minus. Actually, let me write it with the plus. 2 times 0, which is just 0. Before I do that, what should I put on the other side of the 4x minus 7? This is now f prime of x. It's our derivative. We just figured out that this will tell us the slope of any tangent line to that curve. The slope. Not the equation for the tangent line, but the slope. Okay? Now, I want to come back to this next week. No joke, you'll be able to get that in 2 seconds when I show you the rule, okay? And I'm not exaggerating. And you will be like, why did we have to do all that? Let's do this one. Same thing. Or do you want to try it on your own? Yeah, you might. Yeah? You tell me what's better. See it done with, or work with me, or do it on your own? Someone's got to break the tie.
We want you.
Okay. I feel so loved. Okay, this time we're changing it to dy dx. We're going to try the other notation, okay? Just speaking of that, I should have, on this other side, I should have put f prime of x equals all along here. That would have defined what we were doing better, so I'll just add that f prime of x all along there. Probably just need to write it once and then just put equals all down the way. Okay, dy dx. Same thing, Just different notation. This is Leibniz notation. F of x plus h minus f of x over h. So limit as not x, but h goes to 0 of 1 over x plus h squared minus 1 over x squared all over h. Are we good on where that came from? Okay, now we're in algebraic simplification. By the way, the problem on the test like this did not go well. I think 30% of you got it, maybe. So we probably need to practice some fraction stuff. How can we combine those fractions in the numerator?
Copy that.
Dude, you're just pulling stuff out of the air. How do you... That's for division, first of all. Peanut butter sandwiches. I don't know. Let's just throw something out there. No, for real. How do we subtract fractions? What do we have to have? Common denominator. So this left side has an x plus h squared, which means this side needs it. And the right side has an x squared, which means this side needs that. Okay? All right, rewrite all this stuff. Limit as h goes to 0 of x squared minus x plus h squared over x squared times x plus h squared. Does everybody see where the numerator came from? Okay. All over h. Don't forget that, right? Right? Okay. Please ask me about the numerator if you're having trouble with that. Are we good on it? Okay. All right, continuing. I don't know if you're going to like this, but I'm going to switch the over h to 1 over h times. It just makes it less messy. Okay? X squared minus, and then we're going to expand that binomial. So that is x squared, and then minus 2xh, plus 2xh plus h squared. Okay. Any questions on that step? What are we doing right now? Just zooming out a little bit. We are doing the blank to find the blank. Yep, we're taking the derivative so we can find the slope of any tangent line, okay? All right, can we just simplify without writing again? X squared minus x squared, that goes away. So we get 2xh plus h squared in the next line. Don't forget your 1 over h out front. And don't forget that these are negative. Okay, now what? Can we substitute yet and finish out our limit? No, because this h right here is still there. So we need to cancel it out. Do you guys see that we can factor an h off of the right numerator?
Yes.
Okay. This is a good illustration of why your algebra skills need to be good for calculus. Okay, now we can cancel. Now we're not indeterminate anymore. Now we can plug in. Okay, so I'm running out of room. Let's go this way. We do not need the limit anymore because we're about to substitute 0 for h. So we get negative 2x minus, I'm just going to show it even though we don't need to write the 0, over x squared times x plus 0 squared, which is what? Negative 2x over x to the fourth, which is negative 2 over x cubed. Oh, come on. That says negative 2 over x cubed. I'm not sure why it doesn't let me show you. My screen must be calibrated too wide. Maybe I'll see if I can rotate it. Will that help? Yeah. Okay, so that is the equation of what? Actually, I shouldn't have boxed it without writing the dy dx equals negative 2 over x cubed. Box that instead. But anyway, that's the equation for the slope of any tangent line to that weird function, right? So please, please, please make sure that you're saying the slope. This just gives us the slope, that's it, of any tangent line. We still have to go in and write the equation of any specific tangent line. But this gives us the slope. All right, we have time to finish this out. Any questions on those two majorly pain in the neck processes? Okay, by the way, you will be able to do the derivative. You will be able to get negative 2 over x cubed in probably 10 seconds on this one once you learn the rules for it. Okay, so basically the idea is people thought, like Newton, like Leibniz, thought through, hey, let's bring that point closer and make it so close to the other point that we're taking the slope of a tangent line. And then they started seeing, working through this kind of process, which is a pain, they started seeing patterns of how we can do it fast. And that's what we're going to learn in a couple sections, okay? Like, how can we take a derivative without doing that whole definition? And there's those rules for tons of functions. Like, we're going to learn it for lots of things. You will have probably 15 to 20 different rules that you'll just have to memorize. Like, how do we do it for this function, that function? And all of it is faster than this by far. Okay. I do want to remind you, so let's just look at this. We get where we get. We'll see how far it goes. But we're going to always do point slope form in calculus. Okay, point slope form is so much easier than the one you're probably more familiar with, which is slope intercept. Don't do that. It's a pain. Do you guys recognize point slope form? Let me flip back to this way. Does that look familiar? Okay. So x1, y1 is a point on the line. Which point are we talking about when we say a point on the line for calculus? It's the point of tangency, okay? The point of tangency, that's the one we care about. So once we know it, which we'll be given part of that, then we can find this. But here's the calculus version of this. We'll write this and then stop there. I feel like I'm in people's way. Sorry. So we're talking about a tangent to the curve f of x. I didn't read that. The line tangent to the curve f of x at x equals a, just some point that we care about. So it's going to look slightly different than this. Seriously, quit jumping around. Remember, y1, the point that we're talking about, is f of a equals f prime of a. What does f prime mean?
The derivative.
That's the derivative of the function evaluated at a times x minus a. So our slope, like think if I said draw or give the equation of a tangent line to the one of the ones we just did up above. For example, this one on the left, that one. If I said give me the equation of a line tangent to that curve at x equals 4. Well, we just did all this work to find the slope right here of the tangent line. Now we take 4 and plug it in there to get the slope. Then we take that and stick it in here to get the tangent line. Make sense? Okay. So here's what I want. Please try number 5 with those other problems from the first section tonight. And then we'll finish up. Tomorrow I'm going to give you hopefully some time to work. I think we'll have time to work and practice in class tomorrow.